Welcome back. In this segment, we define 1D, 2D, 3D, and multidimensional signals. We also distinguish between scalar and vector-valued signals. We address the question, is a color image a two-dimensional or a three-dimensional signal? Or what's an example of a four-dimensional signal? We will show representative examples of images with different intensity resolutions. For example, binary images, such as a text image, true color images, when each pixel assumes one of 16 million colors, and pseudo-color images, when we decide on the number of colors to be used for visualization purposes for a color, but also for a black and white image, the pseudo-coloring problem. We also show examples of stereo images emulating human perception. That is, we are able to perceive depth since we use two eyes. If we were to use two cameras at some reasonable distance, the so-called baseline, then the two images or videos recorded by the camera emulate our human visual system. We discussed what the term processing in the title of the course means. The narrow definition of a processing system is one that accepts an image at the input and generates another image at the output. The broader definition, however, the one we adopt in this course, is that of a system which, for an image at the input, might generate an image at the output, or a decision based on the analysis of the image, which might result in an action, such as to operate, for example, on a patient if the image is a medical image, or the extraction or segmentation of an object from an image based on its color or its motion and maybe even its classification. So let's look at some of these examples in this next segment. Depending on the number of the independent variables, signals can be grouped, classified into one-dimensional, two-dimensional, three-dimensional, or in general, multidimensional. So tone, speech, audio, biomedical are one-dimensional, typically a function of time. If I look at it as a continuous or discrete, I can call it as S of n, so one independent variable. Text and grayscale images are certainly two-dimensional signals where the independent variables represent space. I can have S, X, Y, for example, I can call it. While color, multispectral, hyperspectral images, we'll say a few words about them, have two spatial coordinates, and then one can look at the amplitude in two different ways. The one is to say that the amplitude is not a scalar anymore, but a vector, a 3x1 vector when it comes to color, since I have three different channels, or a 7x1, let's say, for a multispectral image, or they can be viewed as three-dimensional images with two spatial and one spectral coordinates. Video is a 3D signal. It has two spatial and one temporal coordinates, while a 3D volume has three spatial coordinates, X, Y, Z. As an example of a four-dimensional signal, I can look at a volume, an X, Y, Z signal that changes over time, so time is the fourth independent variable. Some of the tools that we use to describe signals carry over from 1D to 2D to MD. It's a straightforward extension. One just adds one more variable and everything remains the same in some sense. On the other hand, there are certain results that hold true for one-dimensional signals, but they cannot be generalized for higher dimensional signals. Images and videos are clearly the focus of this class, and images are two-dimensional signals, but can be also treated as a three-dimensional when we talk about multispectral, hyperspectral images, while video is a three-dimensional signal, as we already mentioned. So let us look now at some examples, representative examples of signals. Tones are examples of one-dimensional signals. On top you see a sine wave that only has one frequency present in it at 660 Hz. That's why it's called a pure tone. Let us listen to that. At the bottom you see a square wave. It also has the frequency at 660 Hz. However, it has additional frequencies, the so-called harmonic. Let's listen to that as well. It should be clear that the bottom square wave is richer in the sense of having additional frequencies than the pure tone, the sinusoid. Here you have another example of a one-dimensional signal. It's a piano piece, familiar to, I assume, most of you. And this is a synthesized piece, and we can listen to that as well. Here are some examples of images. On the left you see a binary image. That is, I only have 2 bits to represent the different colors. I have a black and a white value here. Binary images, text images like this one, are used in the fax encoding when we want to transmit such text from point A to point B through a fax machine. In the middle you see, again, an 8-bit per pixel image, while on the right is a 24-bit per pixel image. This is a true color image. I have 2 to the 24 different color values. This should be around 16 million different colors to represent such an image. There are different ways to represent the color image, one of which is shown here in terms of 3 different channels, the red, green, and blue channels. This is an RGB decomposition of the image. So each of these channels is a black and white image. I use 8 bits to represent it, so each of the channels has 256 different values, and 8 bits per channel times 3, therefore 24 bits to represent the color image. So if we look at this image, the nose of the mandrill here is quite red, and therefore we see that the pixel values in the red channel are quite high. White is represented by high values, close to 256. Well, it's 0 to 255, so close to 255, while the darker values are closer to 0. So the red nose has high values in the red channel and pretty small values in the other 2 channels. On the other hand, if I look at the cheeks of the mandrill, this is a variation of blue, not exactly the blue color. So I see high values in the blue channel, and relatively smaller values, well, definitely smaller in the red, and somewhere in the middle in the green channel, right? Actually, this particular value apparently is a combination of green and blue. The Landsat program is responsible for the acquisition of satellite imagery of the Earth. It started in 1972, and the most recent satellite, Landsat 8, was launched in this year. Landsat 7 data has 8 spectral bands with spatial resolutions ranging from 15 to 60 meters, and the temporal resolution is 16 days. The main instrument on board Landsat 7 is the Enhanced Thematic Mapper Plus, ETM Plus. The resolution is 30 meters, except band 6 that has 60-meter resolution and band 8 that has 15-meter resolution. Band 8, by the way, is the panchromatic band, so you have low or high rather spatial resolution, 15 meters, while we have low spectral resolution. By the way, this is the visible range of light here. So this is the blue, green, red channel, while the rest are infrared. Landsat data have helped to improve our understanding of Earth, and due to Landsat today we have a better understanding of things as diverse as coral reefs, tropical deforestation, and Antarctica's glaciers. So here's an example of a Landsat 7 image of the city of Amsterdam. Up here you see the blue, green, and red channels, and the rest of the channels, the 4 other channels, are infrared. By the way, hyperspectral images are the ones that have many more bands, up to 200, even 300 bands, but the main characteristic are that the bands are much closer spaced as compared to the multispectral images. Very often, in order to be able to appreciate the Landsat images, the visible bands are combined. This is what you see on the left image. This is, by the way, a Landsat image of the city of London. So these natural-looking images are familiar to human eyes. So the reservoirs here, close to Heathrow, are shown in dark blue, while the city itself is shown in gray. So these images offer very good views of city infrastructure, sediment, and also bathymetry. We can tell how deep the water is over there. However, a band 1.3 image, it's not useful. It's difficult to distinguish between different types of vegetation and between clouds and snow. So therefore, in the middle image, we combine the 3 channels, channel 4, 2, and 3. In other words, 1 infrared band and the green and blue channels. This is a widely used combination that's especially useful for studies of vegetation, since the different types of plants reflect infrared light in different ways. Now, another combination is the 742, shown on the right, so 2 infrared bands plus green, and this combination is especially useful for geological and agricultural studies, because band 7 can help discriminate between various types of rocks and mineral. And bright green here indicates vegetation, while the water appears dark blue or black. Now, our natural world is 3-dimensional, while the images are 2-dimensional. They present the projection of a 3D world onto the 2D plane. In order to perceive depth, we need 2 eyes, so we need 2 cameras that will capture the same scene, and therefore they will emulate the human visual system. So here you see on the left what the left camera sees, and on the right what the right camera sees. And the difference between these 2 images is a so-called disparity map. It tells us how each and every pixel moved from one image, going from one image to the next, or if I use a disparity map, I can map the left image onto the right image. The disparity map relates to the depth in the image. So the 2 channels, if fused appropriately, will give us the depth perception. And the fusion could be done through a red and blue channel, and therefore I can use color-coded glasses, or I can use glasses with different polarization, and so on. Here is another example of a stereo image. In this case, this is a Landsat image. Actually, 2 Landsat images were used that were acquired of the same scene that were acquired 1 year apart. So the satellite does not go exactly over the same position necessarily, and the 2 images represent 2 different images from the left and right channel of the same scene, and therefore they can be combined to give us the depth perception. You can obtain depth information also using the Kinect camera. It projects a known pattern onto the scene and infers depth from the deformation of the pattern. So the Kinect combines structure light with 2 computer vision techniques, depth from focus and depth from stereo. The Kinect is intended to use with the Xbox, and therefore it's of interest there to compute the depth map, but also infer the body position. So you see here the skeleton of the person on the left image, right? So here's the person, this is the depth map, and also the Kinect provides a visible image shown here. So you see the visible and the corresponding depth image that shows where the person stands and where the door is and so on. We can see here a short video that shows both the visible image as well as the depth image acquired by the Kinect camera. Very often we are interested in capturing the three-dimensional structure of an object. So instead of using two cameras, as in the stereo case, we use many cameras on a specific rig. So as you can see here, the image of this particular object is viewed from many different angles. Here's an example of a video. A video consists of individual frames. And one could argue that a video is nothing else than a collection of images, and therefore if I have an algorithm that is effective in processing an image, a still frame as it's called, also I could apply the same algorithm to frame after frame, and I will be done. However, what is special about video is that these frames are highly correlated, and therefore I can gain if in processing such frames I take this correlation into account. Of course, these frames, if they're displayed at some frame rate, 30 frames per second, for example, one can perceive the actual motion in the scene. Finally, processing in the title of the course means the manipulation of the values of an image or a video by a computer so as the resulting image is more useful to us or has some desirable properties. For example, the result of processing might be the removal of blur, as is the case here. You see the input to the system is an aerial photograph that is blurred due to motion between the camera and the scene, and at the output is a sharper, restored image. Now, if an image is input, an image is output, this has been the kind of narrow definition of processing, also referred to as filtering. And the broader meaning of processing that we adopt here is that an image or a video can be input to a system, and we're interested in extracting important features from such an image, or we're interested in making decisions based on the image. As the example here shows, this is a chest X-ray at the input, and based on the analysis that will be performed, whether there is a malignant tumor or not, for example, certain decisions and actions will be the output of the system. As time goes on, what we see is that the boundaries between traditionally separate areas become fuzzy, or in other words, there's overlap between these traditionally separate areas. So when it comes to signal processing, and more specifically to image and video processing that we'll be dealing with in this class, there is overlap between this field and the fields of communication, computer vision, machine learning, and optimization.